In this video, we discuss one of the problems from the Larson Calculus text, 10th edition. It's problem 117 from section 2.2. It asks us to determine the points of differentiability of a particular function. And it's just a couple of functions involving absolute values. So first we're given that y is equal to the absolute or sine of the absolute value of x. Now that can actually be written relatively easily if we remember what y equals the absolute value of x looks like. Y equals the absolute value of x looks like that. And so we can see if we look at this graph that y is equal to x when x is greater than 0, and then y is equal to negative x when x is less than 0. And if you're not really sure, if you don't believe me, look at the graph of y equals x. And then just think about what it means to take the absolute value. Well, the absolute value is the distance from 0, so it's just going to give you the function value back if that number is positive. And then if that number is negative, it's going to make it positive. So it's going to multiply it by -1. So basically what it's doing is it's taking all of these values down here and it's sort of flipping them across the x-axis. And that's why we get that V shape rather than either this line or the corresponding line, y equals negative x. But I think it's sort of easy to see that y equals negative x on that side and y equals positive x on the other. So we're substituting either x into sine of x or negative x into sine of x. When we substitute x into sine of x, well, we just get the typical sine function, which is just like that. Nothing fancy. That is our sine function right there. And the derivative of sine is cosine. So we can take the derivative on that interval as well. Now, on the other side, we've got sine of the absolute value of x, which is negative x, remember. It's negative x here. So we're substituting in negative x on the interval from -infinity to 0. And remember that with our properties for sine of negative x is actually negative sine of x because sine is an odd function. So we can bring that factor of -1 outside of the sine function, and sine of negative x becomes negative sine of x. And so we see that as our graph. I actually prefer this other color. Let's use that one instead. But on this branch, we take the derivative and we get the derivative of negative sine of x is negative cosine of x. And the derivative looks like that. So the question is, where is this function differentiable? Well, I think it's differentiable everywhere except for at x equals 0. The sine function is differentiable everywhere. The negative sine function is differentiable everywhere. But we change the formula at x equals 0 because of the absolute value. And if we look at the derivative graph, which is just this graph right here, which is cosine on one interval and negative cosine in another interval, we see that as we approach x equals 0, we get a limit of 1 from the right of 0 and a limit of -1 from the left of 0. Now, typically we say that that the derivative does not exist at a location like this one, where you've got a cusp here. Because if we look at the tangent lines, or the tangent line on the right of 0, it's going to have a slope of 1, so it's just the line y equals x. And then to the left of 0, our tangent line would be negative x, or y equals negative x. But usually we don't allow ourselves to have tangent lines at cusps. So because of that, we'd say that the derivative does not exist at x equals 0. And that's just a choice, though. We're making that choice. Sort of convention to handle it that way. But if we want to, we could always change that restriction. There is a definition of the derivative that says the limit from the left, if the limit from the left of a particular location of, you know, the slope of the secant line is well defined, then that point can be colored in. We can include that point on our derivative graph. So if we wanted to, we could choose to allow the derivative to actually have two values. It's as if this function has two different tangent lines at x equals 0. So in that case, I would color in those points. And now I've got a derivative, quote unquote derivative, which is not actually a function. It's a function sort of, or it would traditionally be thought of as a function, but it's at x equals 0, it actually has two values. So it's more of a relation rather than a function. So we've got these two values here and here. And if we draw the corresponding tangent lines, they look like this and this. Anywhere else, at any other x value, the tangent line is well defined and it has a well-defined derivative, and that derivative is nice and continuous. But the derivative is discontinuous at x equals 0. And we can choose to allow it to have two function values if we want to, or two values if we want to. And then it would just be a relation rather than being a function. Now, the rest of the problem from the textbook 117 is asking us about the differentiability of the absolute value of sine of x. I think this one is a little bit much more obvious. Let's actually get rid of all of this stuff for a minute. We know what sine of x looks like. Y equals sine of x looks like this. It's that nice curve that's oscillating between -1 and 1 and sort of a regular rhythm to it. Every pi units, it goes back to 0. So we have 0, 1, 0, -1, 0, 1, 0, -1. It's sort of doing that. It's just that constant rhythm. Well, if we take the absolute value, wherever it's positive, it's going to stay positive. So all of these parts of the graph that are above the x-axis are going to stay in the exact same location. But all of these points that are below the x-axis are going to be multiplied by -1. So we're going to end up flipping those pieces up, and it's going to look kind of like a scalloped curve. So we've got that as the graph. And that's very similar to what we saw with sine of the absolute value of x, except rather than having just one point where we've got sort of two tangent lines, now we have infinitely many points where we have two tangent lines. And so at every multiple of pi, we will have the limit from the left for the derivative is equal to 1, or excuse me, the limit from the left for the derivative is equal to -1, and the limit from the right for the derivative is equal to +1. So I'd have a line with a slope of 1 on this side and a line with a slope of -1 on that side. And if we want to, we can view the graph of that. I think I want to get rid of some of the grid lines. I chose some integers between -6 and 6. That's a 13 element list. And I wanted to plot all of those points. Well, actually, we've already labeled the axis, so we don't need to plot those points. Maybe we'll plot the points, but we won't label them. And then the slope is just that cosine of n naught times pi times x minus n naught times pi. So we end up with this sort of, this is what we get at each of these locations at x equals 0, at x equals pi, at x equals 2 pi. Our slope is going to be n naught times pi part of the time. And then it's going to be -1 times n naught pi the other part of the time. So let me graph this as well. So we're missing some tangent lines there. Multiplied by -1 as well. And let's make these another color. I think this is kind of pretty. Now, n naught times pi or cosine of n naught times pi, or cosine of pi times n, where n is an integer, just oscillates. When n is 0, we get cosine of 0, which is 1. When n is 1, we get cosine of pi, which is -1. So it goes 1, -1, 1, -1, 1, -1. And so when I graphed this one, it was giving me a slope of 1 at 0, a slope of -1 at pi, a slope of 1 at 2 pi, a slope of -1 at 3 pi, but it was missing these slopes in the other direction. So I had to also take that cosine graph and multiply by -1 as well. So that way I would take my 1, -1, 1, -1 and multiply it by -1. So it would be -1, 1, -1, 1, -1, 1. It's still just alternating between -1 and 1. Just this one starts with -1 when n equals 0, and this one starts with +1 when n equals 0. So we get that. So that graph. We see this sort of pretty lattice. It almost looks like Argyle socks to me. I thought that was kind of an interesting problem. I hope you like it. Let me know if you have any questions.